Your cells are accumulating damage right now, not from external injuries or infections you can see and feel, but from a chemical process happening inside every cell in your body called glycation. This process occurs when sugar molecules in your bloodstream attach to proteins and fats, creating compounds called advanced glycation end products, or AGGs for short. These AGG compounds are not benign. They cross-link proteins together, making tissues that should be flexible become rigid and dysfunctional. They accelerate the breakdown of collagen in your skin, creating wrinkles and sagging. They stiffen blood vessels, raising your risk of heart attack and stroke. They damage the proteins in your eyes, contributing to cataracts. They accumulate in your brain, where they are implicated in Alzheimer's disease and cognitive decline. And they do all of this whether you feel it happening or not. The problem is that glycation damage accumulates silently over decades. You do not wake up one morning and suddenly notice that sugar has aged your tissues. Instead, the damage builds gradually, year after year, manifesting eventually as the visible signs of aging and the chronic diseases we associate with getting older. Usually in the form of cardiovascular disease that seem to appear from nowhere, cognitive decline that family members notice before you do, or simply looking and feeling significantly older than your chronological age would predict. For the last several decades, we have been told that aging is primarily genetic, that it runs in families, and that there is little you can do to slow it down beyond basic healthy habits, except that research into the mechanisms of aging has revealed that genetics account for perhaps 20 to 30% of how you age. The remaining 70 to 80% is determined by environmental factors, with diet playing one of the largest roles. What we are now understanding is that sugar consumption, particularly the chronic high levels typical of modern diets, directly accelerates multiple biological aging processes through measurable mechanisms that have nothing to do with calories or weight gain. Sugar creates oxidative stress that damages cellular components. It glycates proteins throughout your body, impairing their function. It triggers inflammatory pathways that accelerate tissue degeneration. It impairs mitochondrial function, reducing cellular energy production. It shortens telomeres, which are the protective caps on your chromosomes that determine how many times your cells can divide. And most people have been consuming sugar at levels that guarantee accelerated aging, while believing that as long as they maintain normal weight and exercise regularly, the sugar is not causing harm. Hi, I am Dr. Alex. I am an emergency medicine doctor, and after nearly 10 years in the AANDE, I have seen what accelerated aging looks like when it progresses to medical crisis. The 55-year-old with a massive heart attack whose arteries had aged decades faster than they should have. The patient in their 60s with advanced dementia whose brain had accumulated damage that normally takes decades longer to develop. The diabetic whose chronically elevated blood sugar had created complications affecting their eyes, kidneys, nerves, and blood vessels simultaneously. My goal now is to help people understand the mechanisms connecting diet to aging so they can make informed choices that preserve function and prevent disease. For the next several minutes, we need to understand exactly how sugar accelerates aging at the cellular and molecular level, because once you see these mechanisms, the connection between what you eat and how quickly you age becomes not just plausible, but biochemically inevitable. Before we discuss what sugar does to age you, we need to understand what biological aging actually is. Aging is not simply the passage of time. It is the accumulation of molecular and cellular damage that impairs function and eventually leads to disease and death. This damage occurs through several interconnected mechanisms. The first is oxidative damage, where reactive oxygen species, which are essentially free radicals, damage DNA, proteins, and lipids throughout your cells. The second is glycation, which we have mentioned, where sugar molecules attach to proteins and fats, creating dysfunctional cross-linked structures. The third is chronic inflammation, where your immune system remains in a low-grade activated state that damages tissues continuously. The fourth is telomere shortening, where the protective sequences at the ends of your chromosomes become progressively shorter with each cell division until cells can no longer divide and either die or become senescent. The fifth is mitochondrial dysfunction, where your cellular energy production declines and generates more damaging byproducts. What becomes clear when you understand aging through these mechanisms is that it is not a single process, but rather the accumulation of multiple types of damage occurring simultaneously. Two people of the same chronological age can have dramatically different biological ages depending on how quickly these damage processes have been occurring in their bodies. One person might have the cellular function and disease risk profile of someone 10 years younger, while another might be biologically a decade older than their birth certificate suggests. The difference is largely determined by the rate at which oxidative damage, glycation, inflammation, telomere shortening, and mitochondrial dysfunction have been accumulating, and sugar consumption directly accelerates every single one of these aging mechanisms. Okay, so if you are watching this video, you are probably concerned about aging and longevity, and I just want to take a few seconds here to make you a promise. I promise to keep creating the most helpful videos I possibly can, grounded in science and the latest research to help you understand what actually determines how you age and what you can do about it. All I ask in return is that you give this fairly new channel a chance and hit the subscribe button. If you get to the end of this video and you did not think it was worth your time, or you have not learned something new, then feel free to unsubscribe. No hard feelings, but if you give me your time and your attention, I will give you everything I have learned from over a decade in medicine. So please help me out. Hit the subscribe button to help this channel reach more people like you, and let us continue with the video. So the first mechanism through which sugar accelerates aging is glycation. And this process is so fundamental to sugar-induced aging that the compounds it produces are literally named advanced glycation end products, or AGs. Glycation occurs when glucose or fructose molecules in your bloodstream react non-enzymatically with amino acids and proteins, or with lipids. This reaction does not require any enzyme to catalyze it. It happens spontaneously whenever sugar molecules and proteins are in contact, which means it is happening continuously throughout your body whenever your blood sugar is elevated. The initial reaction produces early glycation products, which can sometimes be reversed if blood sugar drops. But if hyperglycemia persists, these early products undergo further reactions and rearrangements over weeks and months, eventually forming irreversible advanced glycation end products. AGs accumulate in tissues throughout your body, and once formed, they are difficult to remove. They cross-link proteins together, creating stiff dysfunctional structures where there should be flexible functional ones. In your skin, AGs cross-link collagen and elastin fibers, which are the proteins responsible for skin structure and elasticity. As these proteins become glycated and cross-linked, your skin loses its ability to snap back after being stretched, and wrinkles form and deepen. Studies have shown a direct correlation between skin AG levels and visible signs of aging, including wrinkle depth, skin elasticity loss, and overall aged appearance. People with higher blood sugar levels, even within the non-diabetic range, accumulate skin AGs faster and show more advanced skin aging than people with lower blood sugar levels. In your blood vessels, AGs accumulate in the walls of arteries, where they stiffen the vessel walls and impair the endothelium, which is the inner lining of blood vessels that produces nitric oxide to keep vessels relaxed and flexible. When the endothelium becomes damaged by AGs, nitric oxide production drops, vessels lose their ability to dilate properly, and blood pressure rises. AGs also make the vessel walls more permeable to cholesterol, which accelerates atherosclerosis, the buildup of plaque that leads to heart attacks and strokes. This is why diabetics who have chronically elevated blood sugar and therefore higher rates of glycation develop cardiovascular disease at much younger ages and much higher rates than non-diabetics. The chronic hyperglycemia is glycating their arterial proteins continuously, aging their cardiovascular system decades faster than normal. In your eyes, AGs accumulate in the lens proteins, creating the opacity we recognize as cataract. The lens of your eye should remain transparent throughout life, but glycation of lens proteins causes them to clump together and become cloudy. The rate of cataract formation is directly related to lifetime blood sugar exposure. Diabetics develop cataracts earlier and more frequently than non-diabetics, and even within the non-diabetic population, people with higher average blood sugar develop cataracts sooner. In your brain, AGs accumulate in neurons and in the extracellular space, where they contribute to neuroinflammation and neuronal dysfunction. The protein plaques found in Alzheimer's disease contain high levels of AGs, and studies have shown that people with higher blood sugar levels, even those without diabetes, have faster rates of cognitive decline and higher dementia risk. The mechanism connecting AGs to cellular dysfunction extends beyond simple protein cross-linking. AGs also bind to receptors on cell surfaces called RAGE, which stands for Receptor for Advanced Glycation End Products. When AGs bind to RAGE, they activate inflammatory signaling pathways inside the cell, particularly the NF-kappa B pathway, which increases production of inflammatory cytokines. This creates a feedback loop where glycation produces AGs, AGs activate inflammatory pathways through RAGE receptors, inflammation produces more oxidative stress, and oxidative stress accelerates further glycation. This self-reinforcing cycle is one reason why aging appears to accelerate over time rather than proceeding linearly. The damage mechanisms feed into each other, creating exponential accumulation rather than steady linear progression. The second mechanism through which sugar accelerates aging is oxidative stress. When glucose is metabolized for energy in your mitochondria, electrons are passed through the electron transport chain to produce ATP. This process inevitably produces some reactive oxygen species as byproducts, and the amount produced increases when glucose flux through the mitochondria is high. When you consume high-sugar meals that spike your blood glucose, your cells take up large amounts of glucose rapidly and push it through glycolysis and into the mitochondria. This surge of glucose metabolism overwhelms the electron transport chain's capacity to process electrons efficiently, and more electrons leak out and react with oxygen to form superoxide radicals and other reactive oxygen species. These reactive oxygen species damage everything they contact. They oxidize lipids in cell membranes, creating lipid peroxidation products that impair membrane function. They damage proteins, altering their structure and function. They damage DNA, creating mutations that accumulate over time and contribute to cancer risk and cellular dysfunction. Your cells have antioxidant defense systems, including enzymes like superoxide dismutase, catalase, and glutathione peroxidase that neutralize reactive oxygen species. But when reactive oxygen species production is chronically elevated due to high sugar intake, these defense systems become overwhelmed and oxidative damage accumulates faster than it can be repaired. Mitochondrial DNA is particularly vulnerable to oxidative damage because it sits right next to where reactive oxygen species are being generated and lacks the protective histone proteins that shield nuclear DNA. When mitochondrial DNA accumulates damage, the mitochondria produce less ATP and more reactive oxygen species as byproducts of their dysfunction. This creates another vicious cycle where sugar-induced oxidative stress damages mitochondria, damaged mitochondria produce more oxidative stress and less energy, and the resulting cellular energy deficit impairs the repair systems that would normally fix the damage. Over years and decades, this cycle leads to progressive mitochondrial dysfunction, which is one of the hallmarks of aging and a primary driver of age-related disease. The third mechanism is chronic inflammation, which sugar triggers through multiple pathways. High blood sugar activates the NF-kappa B inflammatory pathway directly in many cell types. Sugar consumption, particularly fructose, is metabolized in the liver and generates uric acid as a byproduct. Elevated uric acid triggers inflammatory responses and has been linked to insulin resistance, hypertension, and metabolic syndrome. Sugar consumption alters gut microbiome composition, reducing beneficial bacteria and promoting bacteria that produce inflammatory compounds. When the gut barrier becomes compromised, which happens more readily in the context of dysbiosis, bacterial endotoxins leak into the bloodstream and trigger systemic inflammation. Chronic low-grade inflammation, sometimes called inflammaging because of its central role in aging, accelerates tissue degeneration throughout the body. Inflammatory cytokines impair stem cell function, reducing your body's ability to repair damaged tissues. They promote the accumulation of senescent cells, which are cells that have stopped dividing but remain in tissues secreting inflammatory factors that damage surrounding healthy cells. They impair immune surveillance, reducing your body's ability to clear cancerous cells and infected cells. They damage the blood-brain barrier, allowing inflammatory molecules to enter the brain and contribute to neurodegenerative disease. The inflammatory state created by high sugar consumption does not manifest as obvious symptoms of inflammation like pain or swelling. Instead, it operates at a low level continuously, degrading tissues and accelerating aging processes silently over decades. The fourth mechanism involves insulin and insulin resistance. When you consume sugar, your blood glucose rises and your pancreas releases insulin to shuttle that glucose into cells. Chronic high sugar intake keeps insulin levels elevated much of the time, and cells begin to downregulate their insulin receptors in response to constant insulin signaling. This is insulin resistance, and it has numerous aging effects beyond its role in diabetes development. Insulin is an anabolic hormone that promotes cell growth and division. In the context of adequate insulin sensitivity and appropriate insulin levels, this supports tissue maintenance and repair. But chronic hyperinsulinemia, which is elevated insulin levels, promotes excessive cell division and growth in ways that accelerate aging. Insulin activates the mTOR pathway, which is a nutrient-sensing pathway that promotes protein synthesis and cell growth. Chronic activation of mTOR accelerates aging through multiple mechanisms. It reduces autophagy, which is the cellular recycling process that clears damaged proteins and organelles. When autophagy is suppressed, damaged cellular components accumulate faster. mTOR activation also promotes cellular senescence, where cells stop dividing but remain metabolically active, secreting inflammatory factors. Studies in multiple organisms have shown that reducing mTOR activity extends lifespan, while chronic mTOR activation accelerates aging. The high-sugar, high-insulin environment of modern diets keeps mTOR chronically activated, accelerating the aging processes that calorie restriction and intermittent fasting slow down by reducing insulin and suppressing mTOR. Insulin resistance also impairs growth hormone and IGF-1 signaling in ways that promote aging. While excessively high IGF-1 promotes cancer risk, very low IGF-1 impairs tissue repair and maintenance. Insulin resistance creates a situation where IGF-1 signaling becomes dysregulated, neither optimally high for repair nor appropriately low for longevity benefits. Additionally, insulin resistance in the brain has been specifically implicated in Alzheimer's disease, which is sometimes called type 3 diabetes because of the strong connection between brain insulin resistance and neurodegeneration. The brain requires insulin signaling for neuronal function, memory formation, and clearance of amyloid plaques. When brain insulin signaling becomes impaired due to systemic insulin resistance from chronic sugar consumption, cognitive function declines and Alzheimer's risk increases dramatically. The fifth mechanism is telomere shortening. Telomeres are repetitive DNA sequences at the ends of chromosomes that protect the coding regions of your DNA from degradation during cell division. Each time a cell divides, the telomeres shorten slightly because the enzyme that replicates DNA cannot fully copy the very ends of chromosomes. When telomeres become critically short, cells can no longer divide and either die or become senescent. Telomere length is considered one of the best biomarkers of biological aging, and shorter telomeres are associated with higher rates of age-related disease and shorter lifespan. Multiple studies have now shown that higher sugar consumption and higher blood glucose levels are associated with shorter telomeres. The mechanism appears to involve oxidative stress and inflammation, both of which accelerate telomere shortening. Additionally, high blood sugar and the oxidative stress it creates damage telomerase, which is the enzyme that can add sequences back to telomeres and slow their shortening. In cells where telomerase is active, this damage reduces the enzyme's effectiveness. The glycation of telomeric DNA itself also appears to make telomeres more susceptible to degradation. The result is that people with high sugar intake and elevated blood glucose have accelerated telomere shortening compared to people with lower sugar intake and better blood sugar control. This translates directly into faster biological aging and earlier onset of age-related diseases. Studies comparing people of the same chronological age have found that those with higher sugar consumption have telomere lengths corresponding to people several years older. Now, the critical question is, what level of sugar consumption actually matters? The aging mechanisms we have discussed occur on a continuum. They are not binary processes that suddenly activate above a certain threshold. Every elevation in blood glucose creates some glycation, some oxidative stress, some inflammation. However, the dose makes the poison, and there are clear inflection points where damage accelerates significantly. Blood glucose levels above 140 mg/dL after meals are where glycation rates increase substantially. This is why the diagnostic criterion for diabetes includes a 2-hour post-meal glucose above 200, and pre-diabetes is defined as levels between 140 and 199. But even levels that spike into the 120 to 140 range, which is common after high carbohydrate meals in people not diagnosed with diabetes, create measurable glycation and oxidative stress. The amount of added sugar in typical modern diets far exceeds what human metabolism evolved to handle. The average person in developed countries consumes roughly 15 to 20% of their calories from added sugars, which translates to 60 to 80 grams daily. This is in addition to the natural sugars in fruit and the carbohydrates that break down into glucose from grains and starchy vegetables. The constant elevation of blood glucose from this level of sugar intake keeps glycation, oxidative stress, and inflammation running at rates that accelerate aging measurably compared to populations consuming lower sugar amounts. Population studies consistently show that people in cultures with low sugar consumption have longer lifespans, lower rates of age-related disease, and biological markers suggesting slower aging even when other factors like genetics and activity levels are controlled for. When we understand how sugar accelerates aging, we simultaneously understand what slows aging down. Biological age reversal, or at least dramatic slowing of the aging rate, occurs when several things happen. The first is that blood glucose levels are stabilized within optimal ranges, minimizing glycation and oxidative stress. The second is that chronic inflammation is reduced through multiple pathways. The third is that insulin sensitivity is restored, allowing appropriate insulin signaling without chronic hyperinsulinemia. The fourth is that mitochondrial function is preserved or improved through reduced oxidative stress and adequate nutrient support. The fifth is that telomere shortening is slowed through reduced oxidative damage and inflammation. Every intervention that genuinely slows biological aging works through one or more of these mechanisms. Reducing sugar intake is the most direct intervention. Limiting added sugars to less than 10% of calories, and ideally less than 5%, substantially reduces the glycation load and the oxidative stress from glucose metabolism. This means consuming fewer than 25 grams of added sugar daily for most people, and being aware that sugar appears in countless processed foods under dozens of different names. Reading ingredient labels and avoiding foods with added sugars as one of the first few ingredients eliminates most of the problem. Replacing high-sugar foods with whole foods that contain fiber, protein, and fat, along with any carbohydrates, dramatically reduces the blood glucose spikes that drive glycation and oxidative stress. Exercise is another powerful intervention because it improves insulin sensitivity, allowing glucose to be cleared from the bloodstream more efficiently with lower insulin levels. Exercise also activates cellular cleanup mechanisms, including autophagy, helping clear out glycated proteins and damaged cellular components before they accumulate. Resistance training specifically helps by building muscle mass, which is the primary tissue that takes up glucose from the bloodstream. More muscle mass means better glucose disposal and lower average blood glucose levels. Cardiovascular exercise improves mitochondrial function and reduces oxidative stress production per unit of glucose metabolized. Dietary choices beyond sugar also matter significantly. Consuming adequate antioxidants from colorful vegetables and fruits provides your cells with the compounds needed to neutralize the reactive oxygen species produced during sugar metabolism. Polyphenols from berries, tea, and dark chocolate activate cellular stress response pathways that upregulate your endogenous antioxidant production, providing protection that exceeds what dietary antioxidants alone could achieve. Omega-3 fatty acids reduce inflammation and protect cell membranes from oxidative damage. Adequate protein provides the amino acids required to synthesize glutathione, your master antioxidant, and to repair glycated proteins that can still be salvaged. In emergency medicine, we see the end result of sugar-accelerated aging when it progresses to acute medical crisis. The patient in their 50s with a heart attack whose coronary arteries are as diseased as we would typically expect in someone 20 years older. The diabetic whose chronic hyperglycemia has created such extensive AG accumulation that they are experiencing kidney failure, retinopathy causing blindness, and peripheral neuropathy causing pain and loss of sensation in their feet. The patient with advanced dementia in their late 60s, whose brain has accumulated decades worth of glycation damage, inflammation, and amyloid plaques in an accelerated time frame. These cases represent failure of the body's aging management systems, and sugar has been a primary driver in nearly all of them. What becomes clear from clinical medicine is that biological aging is not destiny. The patients who age well, who come in for minor issues in their 70s and 80s with the physiology and disease risk profile of people 15 years younger, almost universally have maintained low sugar diets throughout their adult lives. They do not consume sodas regularly. They do not eat desserts daily. They do not snack on processed foods loaded with hidden sugars. Their lifetime exposure to elevated blood glucose has been minimal, and correspondingly, their accumulation of AGs, oxidative damage, inflammation, and all the other markers of biological aging has proceeded slowly. They look younger, function better, maintain cognitive clarity, and avoid the chronic diseases that we mistakenly attribute to aging itself, rather than to the accelerated aging driven by dietary choices. So where does this leave us regarding sugar and aging? The evidence is unambiguous that sugar consumption directly accelerates multiple mechanisms of biological aging through glycation, oxidative stress, inflammation, insulin resistance, and telomere shortening. These are not theoretical concerns or correlations that might have alternative explanations. They are direct cause and effect relationships demonstrated in cellular studies, animal models, and human trials. Every gram of sugar you consume creates some amount of these aging processes. The question is not whether sugar ages you, but how much aging acceleration you are willing to accept in exchange for the palatability and convenience of sugar-containing foods. The threshold where sugar consumption transitions from minimal impact to significant aging acceleration appears to be somewhere in the range of 25 to 50 grams of added sugar daily. Below this level, particularly when combined with exercise and adequate micronutrient intake, your body's repair and antioxidant systems can largely manage the damage. Above this level, particularly as you approach the 75 to 100 grams daily that many people consume, the damage accumulates faster than it can be repaired and biological aging accelerates measurably. The difference over decades between someone consuming 20 grams of added sugar daily versus someone consuming 80 grams daily is likely measured in years of biological age and significant difference in disease risk and functional capacity in late life. This does not require perfection or complete elimination of sugar, which would be impractical and potentially create more stress than benefit. It requires awareness of how much sugar you are actually consuming, which for most people is far more than they realize because sugar is added to so many processed foods. It requires making deliberate choices to minimize added sugars while focusing on whole foods that do not spike blood glucose dramatically. And it requires understanding that these choices compound over time. The glycation, oxidative damage, and inflammation you prevent today do not just benefit you today. They prevent damage that would have been irreversible and that would have accelerated further damage in the future. Every day of lower sugar consumption is an investment in slower biological aging that pays dividends for the rest of your life. And finally, just to end, please subscribe to the channel if you found this useful to help me reach more people like you.